of derivative-free optimization today. And unfortunately, because we don't really have that kind of time, I could, at least as far as optimization is concerned, cover not even 1/10 of what I would have liked to cover in the class, but so you get to see a little bit of eclectic presentation with a very biased kind of optimization presentation. Most of the optimization stuff, except the fixed point theory that I briefly mentioned, most of it is very targeted to the machine learning style of optimization. But there's a lot more. I might briefly mention on Wednesday a list of some topics that we could have covered, but maybe someday in the future, if you look at my next class on online, you'll get to see some more interesting topics. So today I'm just going to talk about a little bit about derivative-free optimization. To some degree, you have already done some amount of optimization without resorting to derivatives. And without resorting to derivatives, I mean neither gradients nor subgradients. So implicitly, the trivial most version is this that you've already done, which we call coordinate descent. You minimize f over coordinates. So here it is, of course, fraudulent. To do this minimization, you might do it whichever way, but I'm not explicitly invoking any derivatives there. Of course, analysis of this thing without explicitly invoking derivatives is quite tricky even now. But it requires, just to implement that, you need a subroutine that can minimize over any of those coordinates, which means you need to be able to explicitly access your function f, if not in its entirety, at least coordinate by coordinate. So that is very specialized kind of access that you're requiring into your function. Of course, if this function f of x has been written by you, you can easily build such access, not a big problem. But it's not always possible, and sometimes it's not even practical. So that's why people have cared about for many years. This is an old field called derivative-free optimization. And some of the motivating things are that sometimes f of x is computed for you by a binary executable file, because legacy software was implemented by some Fortran programmer back in the day, and you only have access to the binary. You don't have f of x, but you still want to deal with that. So that used to be one of the most typical setups. It's not so common for us, but there's a very large body of numerical code out there which really is of that style. And these are more excuses of lazy people, because it's painful to maybe sometimes compute gradients, so let's be lazy. But some other things, this is the implementation part. Whether you want to spend a lot of time nicely implementing gradients, or you're in a rush and rather just save your time and let the computer do the work. So most of these are lazy people's excuses, except some important black box stuff like that. And sometimes if you have non-smooth, non-convex functions, we don't really have a good way to differentiate these, but we could still try to minimize these without using derivatives, or maybe by sort of simulating the derivatives of these difficult functions. So that's another setup, and that was the biggest motivation. So its derivative-free optimization is somewhat, or rather quite uncommon in the world of machine learning, because as you'll soon see from the kinds of theorems that come out, the dependence of these methods on problem size is somehow disappointing. We cannot really afford to pay that kind of price. It has been around for a long time, but very interestingly, its complexity theory or convergence rate analysis, all of this is very recent, once again from Yuri Nesterov in 2011. So this field has been around for quite some time, but understanding it theoretically is recent progress. So, but I hope that someday we get to see some more Dfo related progress even within machine learning. And one place where people do use this, we don't do that much, say, in machine learning, but in other areas within computer science, people often build big simulators, whether it is for computer architecture, compiler, or whatnot. when trying to optimize big simulation-based systems which have a few hyperparameters, you might try to invoke Dfo there. So that's one place where it could be used. Anyhow, I'm still waiting to see at least one Dfo application in machine learning. Let's see when that happens. Maybe you imagine up one. And before we turn to Dfo, important warning, right? If you have the ability to compute derivatives and gradients, go for it, do them, use them. Don't resort to Dfo. So that's the caveat. But it's an important warning, okay? So some things that I'm not going to discuss today, but worth mentioning. There's a very well-developed body of work on automatic differentiation. You can type your function in C, pass it through an automatic differentiator, it will generate C code which computes the gradient of f. So it's good for lazy people. And it's a fairly well-developed area, code generation, automatic differentiation. This is just one of the websites, but you just, once you know the keyword, there's hundreds of things related to that. Back in the day, in theoretical CS, let me actually show one of these papers. There's an area called fast differentiation. So I asked Yuri Nesterov about this last year. And in fast differentiation, Bauer and Strassen had showed in 1983 that if you have an arithmetic circuit up to some, allowing some degree basic computational operations that can compute f, from this circuit you could realize a circuit that computes gradient in at most 4 times the complexity. Of course, it's not for arbitrary f, there are some restrictions, but it is quite a powerful result. And a more general version of this is in a paper by Kim Nestrom Cherkassky. And when I asked, I contacted Yuri to ask him if there's been any progress on this. So this stuff is called fast differentiation. It requires much more storage, but you can do it. Theoretically, there has not been that much progress. I'll just flash a little paper here, which summarizes, which is actually quite an interesting paper about a recent paper from 2007. And in case you're interested in theoretical questions related to cost of estimating derivatives, it's an interesting paper on the complexity of the gradient of rational functions. So here also the aim is essentially, if you have a circuit for computing rational functions in order t time, then within 4 times or 7 times t, you can get the gradient. I don't have time to talk about this, but it's quite interesting from a theoretical CS perspective. Okay. So I'm also not going to discuss non-convex Dfo today. And for those who are interested in the kind of collection of what is known about Dfo or pseudo state of the art of Dfo, there's a book called Introduction to Dfo it's from 2009. So these are the kinds of things I'm not going to talk about today, but they're there for your reference. I'm going to talk about something maybe simpler, but it's essentially coming from Yuri's paper, which I cite at the end of the lecture. And let's build up a little bit. Couple of ways of doing Dfo. The first one is brute force. And this brute force is also has been fine-tuned to make it more sophisticated brute force. So you try to minimize f of x. What would be the most brute force method that comes to your mind? You want to minimize f of x, and I only give you ability to compute f of x at at any arbitrary x within your domain. So how would you go about minimizing such an f? Pardon? So I started some x. So you're maybe doing something more clever. So this is one brute force. Generate some random vector x or y. See if it decreases the objective function. This is your new point. Otherwise, just repeat. So this is super stupid, right? People have proposed this and maybe even written a paper about this. So it can happen. But more interestingly,
what if we compute numerical gradients?
Yeah, so that is slightly more interesting, and that version has also been done. So we are going to look more closely at the idea of numerically approximating the gradient. So finite differencing is something which I mentioned also on the previous slide. It is often used, and we'll see what we can do with that. But the reason I'm mentioning this is that this brute force is not completely idiotic because it gives a nice idea. So this one is picking a y agnostic of all the previous x, or it's not really building a model of what's going on. But there is a more clever, much more well-developed area called Bayesian optimization, probabilistic optimization, which builds a good idea of what the landscape looks like and samples for values in a region of high uncertainty, low whatever, to try to, using Bayesian logic, zoom down into where your global minimum of a difficult function might lie. So these are clickable links, by the way. So if you click in the PDF, you can check that link out. And people in several areas do regularly study Bayesian optimization. Even I think at NIPS 2013 there was a workshop on probabilistic numerics, so some of it might find its way in there also. So it's so this is an interesting idea. Anyhow, so let's look at something else, simulating gradients, right? That's the thing that actually anybody would have as a first guess if they know about gradients. So one choice is you pick some unit vector at random, or you could pick some other vector at random. I'm just mentioning one that people have tried previously, and this one will become slightly clear as we progress. So this one says we sort of compute finite differences, but f is a real valued guy, right? But gradient is a vector. So somehow you want to actually get out a vector in which direction to move. So you take this finite difference multiplied by u, that's sort of your direction. It's in the flavor of our randomized methods. If this thing kind of simulates a gradient, we are fine. And that's really what we are getting at. So if that finite differencing width interval mu goes to 0, then actually this quantity becomes directional derivative in the direction u. So this is not entirely yet, and if f is differentiable, that's just the directional derivative. So ultimately what we are trying to do is, if the expectation of that object under randomization generates a subgradient or a gradient for us, then we are in great shape. And that's sort of what we want to try to do. And directional derivatives are good because they are numerically reasonably well approximable by finite differencing. So even you can automate a lot of this process. Okay, so now what there are two views of this previous iteration that I showed you. So this iteration with gk, where gk for me is just that, directional derivative in that random direction, I could view that as some kind of stochastic subgradient for me, if that expectation on the previous page was correct. So one way of viewing this derivative-free optimization, f is actually a deterministic function, but we are generating a stochastic gradient for it. So you can think that your oracle, which spits out gradients, has randomness in it, and it corresponds sort of to an optimization problem where your f of x may be viewed as an expectation of suitable. So we've seen this in stochastic optimization previously. And in the analysis of typical stochastic optimization methods, we assumed things like the variance, or sorry, not variance here, that second moments of your stochastic gradients are bounded because it comes up in the analysis. I think I went through one of these proofs where this bound was used. So in Yuri's paper, he makes an interesting point here, that instead of going through that route, he says in our case, if f is actually differentiable, then this object in expectation is actually the gradient, and its second moment is bounded by that quantity. There is one bad thing about that upper bound, that this This bound here is just some universal constant on the entire domain. This upper bound depends on the dimensionality. So this leads to maybe a simpler algorithm, but it already indicates. So this is a non-trivial theorem actually. I'm not going to prove it today. But this indicates that in the absence of access to an oracle that generates honest gradients for you, if you're generating them essentially by simulation, essentially an order n times extra dependence on the dimension comes up. Now hand-wavily, it is kind of believable, because if you were to simulate, there are n dimensions, if you were to simulate the n different partial derivatives by some kind of differencing, you have some order n time extra effort going on. And that's in some sense the difficult price that comes up. I don't know right now, and that's part of the open questions here. Maybe for certain nicer classes or certain nicer specific examples of f, this dependence could be improved. However, that type of analysis is mostly academic, because when are we going to really use DFO? When we do not know too much about f, right? So you can make the analysis look nicer, but it might not really correspond to the reality of where you would be using DFO. Okay, so one of the key ideas, yeah?
So let's say the function is not actually differentiable. What guarantees are there for this simulated gradient?
Yeah, so if function is not differentiable at all, that's where actually to make the DFO procedure work, that's where the next slide comes up. That's the most important idea here, is instead of optimizing f, we smooth f, and we optimize you can say we optimize the smoothed f. And smoothing f is essentially like convolving it with something that has a nice density. And when you convolve things, the smoothness of the resulting thing is at least as good as the smoothest of the two. And so this idea, we'll go through the actual math of proving that this is nice. And that's really the most important part. The others are somewhat ugly details or heavy algebraic details that you can read in the paper if you're interested. So the idea here is you take whatever f, you smooth it. And the smoothed function has much nicer properties. And we'll look at that. So if f is a deterministic function, this is one DFO method that we will look at. However, this DFO method relies on being able to compute a directional derivative, right? So if you don't have an oracle that can do that, then you have to approximately simulate that oracle, because a directional derivative can be, as we saw on the previous slides, approximated by these finite differences with small enough differences. So this is like the practical finite differencing version. And you already see very bad stuff in here, which displeases me, and which also shows you why nobody in machine learning really cares about this DFO world. And even in the practice, people usually don't solve DFO problems for more than 100 dimensions. The complexity dependence on n is the number of dimensions, not the number of data points, is quite large. But it's important, this is the first time in 2011 that actually somebody managed to give an analysis, complexity analysis of DFO at all, and some of that almost indicates also lower bound level stuff in there. So it's important in that respect. And the DFO world also applies even if your black box itself is stochastic. So far you can have a deterministic f of x to which you only have a zeroth-order oracle, and you're trying to simulate its gradients. You could also be trying to minimize an f of x which itself is stochastic and is still available via a black box. So there's two levels of difficulty involved in there. But whatever I say for the non-stochastic part, more or less all of that goes through also for the stochastic part, because the smoothing is a really nice thing. So let's look at some basic setup. If you want to maybe follow along, you don't want, then you can, if you are on your laptop, you could let's see. A lot of it is based on, what I'm talking is based on this paper by Yuri Nesterov on random gradient free minimization of convex functions. So I cite this only at the end, but you can look at it right now if you want. And most of what I'm talking is, now that I'm talking is simplified from this paper. Okay. So the setup is, we are doing minimization in a Euclidean space. Let it be, call it E. This simplifies notation. It saves me from writing R to the N each time. So E basically means R to the N. And the norm in there, instead of giving, so the norm in there is not just x square, it is x transpose b half x. That's just simplifies, it just gives a general notation. Okay, so these are the two norms we are using. So that's the Euclidean space over which we are minimizing. So this is the original norm, this is the dual norm. That's why it's written with a G star. So B is a positive definite matrix. So we've met our function classes. The function classes of interest today are f is C0 Lipschitz. So f need not be differentiable, but it has a Lipschitz constant L0. And that's what it means. Or f is once differentiable with CL1, and that's what it satisfies. And we've already proved, or equivalently you can show that descent lemma. So that's the setup. Now let's see that this Gaussian smoothing. So we were, previously I said we smooth by convolving it with a nice density. Now let's maybe do the simplest kind of density. Let's do a mean zero Gaussian. And I just cleaned the notation a bit. Just always remember throughout here that for us U square is U transpose BU, which I sometimes write as BU. It just hides the B inside that integral, okay? So that it looks like a spherical Gaussian. So the smoothed F is that, and kappa is normalization constant. So that's all, it's whatever 1 by 2 pi determinant, etc. And the key point of using the smoothed thing is that the smoothed function is in some sense nicer than the arbitrary f. How exactly you use that smooth function comes much later. It's also up to your imagination. But let's first study that this smoothing is a nice idea. And this smoothing idea has also been used previously for stochastic convex optimization in a paper by Ducci, Bartlett, and Wainwright, where they actually assume access to an oracle that can generate subgradients, but it's non-smooth, but they smooth it. We are not assuming access to an oracle that generates subgradients. We are just smoothing it because we are doing Dfo. So let's look at why is the smooth function nicer. So the first thing, if f is convex, then the smooth function is also convex. That part is trivial for you to prove. It's just a non-negative linear weighted combination. So that's easy. F of x is upper bounded by the smooth function, which also intuitively makes sense. You're adding a little bit of perturbation, but it's a Gaussian perturbation. Things should be able to go in both directions, but why is it? So why is this true? It's not immediate. Means it is immediate as soon as you write it down, but let's see. So suppose G is any subgradient, then just plug in what is f mu of x, that's our smooth function. And what should you do now to prove that lower bound? This is a hint, right? If f is convex, then you just use the definition of subgradient to write that lower bound. And because everything is non-negative, you can still continue writing that inequality. And now, very nice thing happens. It's a mean zero Gaussian, so the linear term disappears. And by now, I think in this class, including what the stuff that Alex has talked about, you have maybe exploited the mean zero Gaussian too many times already. So this is another example. So that's good. Now let's begin to see some other cool properties of the smooth function. If f is Lipschitz, then the smooth guy is Lipschitz, in fact with a smaller Lipschitz constant. So in some sense, smoothing damps out crazy oscillations, and even though f is convex, it's not going to really oscillate, but the amount it can sort of vary, that gets damped out by smoothing, and you can prove that. So that part is also easy to prove, but it's a really nice property. So let's look at that. So just look at the definition of Lipschitz. So I applied the triangle inequality already once to take the absolute value inside the integral. Now f is Lipschitz, so the next line is immediate, right? And after that, the last part just integrates out to 1. So this is just an upper bound, which means the true Lipschitz constant of the smooth guy is going to be smaller than that. So which is a nice property. You can also similarly do a little exercise to see that if f is actually differentiable, then the gradient also inherits a Lipschitz constant. We'll look at this more precisely soon enough. So now we got that the smoothed function is, but while bounding on how well an approximation, how good an approximation f mu is, we need to maybe control not only lower bound or also an upper bound. So fx plus what? And so essentially we are trying to see how far, because this sandwich inequality tells you essentially how far is f from f mu, and you'd like to know that. Of course, it is going to be a function of the density with which you're convolving. If the density is crazy, then that should show up here. Let's see how the Gaussian shows up. So you look at that distance. So far, so good. If f is Lipschitz, you just invoke the Lipschitz guy there. You get mu L0 of f and this integral, right? After invoking the Lipschitz inequality for f. Now, what does this do? We need to then estimate the value of this integral. That's all we need to do. So let's look at a slightly more general thing. Let's look at these moments of the norms of u for p bigger than or equal to 0. And let's try to get a handle on those moments. With p equal to 1, we'll be able to get an idea of that, get an upper bound on that. I really like this cute little proof that Yuri has in his paper. So let's look at it. So the trivial cases, if p is 0, then of course theta of 0 is just 1. That's by definition. If p is 2, you're looking at that second moment. That is actually equal to n, the dimensionality. Why is that? Let's maybe go through a short proof. Or you might want to prove it yourself. So this is, okay, let's just, let me go through it slowly here. This is essentially Yuri's proof. That if you look at the log of that integral, remember this u is given by this inner product, right? That thing integrates out to nothing but the normalizing constant of that Gaussian, and once you take the log of that, that's what falls out, right? That's just the log of the normalizing constant of the Gaussian. So far so good? Now you differentiate both sides with respect to b. So you differentiate, you differentiate this side with respect to b and also that side with respect to b. Once you do that differentiation, the denominator will become 1 because log, when you differentiate that, that goes down and the numerator gets differentiated to that object. The right hand side is b inverse. And now multiply both sides by b. Right hand side, so there's a minus sign that comes from here, that minus cancels with the minus that comes from that. So you should work out through that little simple algebra. It's a very cute proof. Now if you multiply both sides with b, on the left hand side you will get that along with the integral, which is in our notation nothing but the u square with that integral. And the right hand side becomes identity, then you just take the trace.
So just to be clear, u star is
transpose, sorry.
Isn't it du transpose? Because then, like, otherwise, I'm not sure if you can.
Oh, maybe I maybe missed out on a b when I differentiated that guy. Yeah, you're right. I'm sorry. There should be a b coming from there. You are right. You are right. Anyhow, so two moments are controlled, but the nice thing happens now. That's the very simple observation, but a very nice observation. That theta p function, which we defined as the pth moment of the norm, is log convex in P, which is obvious, right? So why is it log convex? Yeah, so it's just a summation of non-negative linear combination of log convex functions. So, which leads to a nice proof that for p belongs to 0 to 2, theta p is upper bounded by that. For p bigger than 2, there is more complicated bounding, so I'm not going to talk about those. So how does the first bound follow? Well, since log of theta p is convex, just write p in that interval as a convex combination of the endpoints and apply log convexity. And you already know the values of theta at the endpoints. Hence, by nicely using log convexity, you have a cute little bound for theta p. So this is nice because now we know what theta 1 is upper bounded by. Theta 1 is upper bounded by square root of n. And theta 2 is upper bounded by n. So you have some control on these moments. Okay, so now we'll use that to prove the result, that how far is f from f mu. So we already did that. Sorry, I forgot to put the absolute value signs on the right hand side. So far we had already reached, and now this integral we have upper bounded by square root of n. And hence you have showed that this is essentially the amount of distortion you incur by smoothing. So it is still nasty to have a dependence on square root n. That means you cannot over smooth because this thing will become quite large. But this also suggests that the amount of smoothing mu, if you want this to be independent of dimension, the smoothing has to be tiny. It has to be a function of essentially order 1 by root n. So there will always be this trade-off. Smoothing makes the things nicer, but it incurs some distortion. If you want, so you have to do a sweet spot trade-off. How much nicer do you want things to be and how much distortion can you tolerate? And this kind of gives insight into the level of smoothing you can work with. So even nicer, if f is actually differentiable, then the smooth version depends on Lipschitz constants of the gradient of f, which might be smaller than the Lipschitz constant of the function, but the dependence on dimensionality increases. But here again, the nice thing to notice is that mu is sort of like 1 by root n for n to disappear. So that dependence, even for differentiable functions, you don't get an improved dependence or improved behavior of mu on n. So to prove this, you can again follow the same exercise. And here you just use the upper bound on the second moment. Fine. So the reason it's called smoothing, or why people have actually considered Gaussian smoothing or smoothing for long, is if your f were non-differentiable to begin with, f of mu is still going to be differentiable. So you can start with a non-smooth function, not go too far from it. You already saw how far you go from it, but actually get an f of mu which is differentiable. This is also the kind of thing that is exploited in this stochastic optimization by smoothing paper of Ducci, Bartlett, and Wainwright that I mentioned. So if f is C0 Lipschitz, then f mu actually has a CL1 Lipschitz constant, and we'll try to see also how big L1 is. So in fact, again we see the same fight between mu and root n. So the Lipschitz constant here, no, actually this blows up mu's in the denominator. The Lipschitz constant here could be somewhat large. So if the smoothing is very small, which also makes intuitive sense, right? If f is non-smooth and you barely smooth it, then the Lipschitz constant, which tells you how wildly the gradient can vary, is going to be large. And it depends as order 1 by mu on the smoothing. So that's why if you want a more smooth function, then the smoothing had better be large, which is a tautological thing to say, but this is exactly the dependence.
But isn't the smooth function, once you convolve it, isn't it necessarily smoother than the initial function, the original function?
Yeah. Means we can see here, oh, you are saying if the initial function is also smooth already?
No, regardless of whether it's smooth or not, like once you convolve it, it's necessarily smoother than the previous.
Yeah, so the thing is, this statement is exactly answering that question. What do we mean by smooth? For the purpose of this class, we agreed on the definition that something that is at least once differentiable, we'll call it smooth. And here the original function f need not be differentiable, but f of mu is now once differentiable. And it's not only once differentiable, its derivative has a controlled Lipschitz constant. So it's actually a fairly well-smoothed function. You can experiment for your entertainment non-Gaussian smoothing with other densities to see if you can get better control or better behavior on mu. I haven't tried it, but I don't really think we will benefit too much from non-Gaussian smoothing. Unless it happens to, but I'm not saying forget about it. This is just one, it's just that I guess ultimately integrals with Gaussians are easier. That's why most people would stick to this kind of smoothing. But it's not the only way to smooth things. And maybe it's good to also sometimes think that there might be other ways of smoothing quantities, because suppose you were in a setup where everything, where f of x, so here, yeah, I think it's good to mention already here. So when we are smoothing f mu of x was using f of x plus whatever mu times u, and u is generated according to a Gaussian, right? Now suppose your black box function short circuits the black box if you try to give it a negative input. The Gaussian smoothing at a given x could make the argument of f of x negative depending on how big that is, right? So you could be in a setup where physical restrictions on your system do not allow you to do Gaussian smoothing. So it's not the only smoothing to worry about. Depending on your reality, you might think of other notions of smoothing. But the analysis might become messier. But it's good to remember that this is not the only way to go about smoothing. Okay, so let's try to get the gradient. Let's see what gradient of f of mu is. So f of mu, this is the definition. So I'm just rewriting it. I'm just making a change of variables here in the integral. Integral is over u. I'm going to make a change of variables to y. So there will be a mu to the power n term, which comes from the Jacobian of the determinant when you make a change of variables. So you make that change of variables to write the integral in terms of y. And then you differentiate that with respect to x. So this is a differentiable function of x. You differentiate it with respect to x. That's the kind of stuff that falls out. Okay, so that's what it's looking like so far. Now we again use the fact that we have a mean zero Gaussian to be easily able to subtract out f of x times the rest of the stuff. So I'm just highlighting this. This is sort of like a finite gradient, finite difference. Fine. But let's actually see that whatever we did is a meaningful thing to do. So I'm just using that shorthand. So let's try to look at see if this is Lipschitz continuous gradient, the smooth guy. Well, we just plug in the stuff that we got on the last slide. I just wrote that because it wasn't otherwise fitting in one line. The dp of mu is just the rest of the Gaussian measure there. So now you just apply the triangle inequality and Cauchy-Schwarz. You get that little thing out. Oops. And now you just collect. Now you apply the triangle inequality to this thing twice, to this once. So you get the factor of 2 there times the Lipschitz constant of f. That's what will come out. Kappa and mu are already there. And okay, one thing that I don't know what I did with the b there. I'll have to, where did I send the b? Okay, I'll have to double check what I did with the b, or if the b was supposed to be there in the first place or not. But modulo that little error of mine, the rest of the analysis is exactly as it should be. And we get to see that this f of mu actually has a Lipschitz gradient with a reasonable Lipschitz constant. It's not entirely reasonable because it depends fairly strongly on the dimensionality, but at least it's just square root n dependence, not complete order n dependence. So this kind of shows that now you have a smooth function, and the rest of the stuff is essentially, so all of these little facts about the smooth function are then used subsequently in a method which actually optimizes without using derivatives. So simulated gradient, some things that we've already seen. So the directional derivative was given by that. So in reality, you can approximate it using some finite differences like that. As for mu equal to 0, what you can actually prove, which is a nice little exercise, is we had f mu of x. We had shown on some slide, let's actually look at that slide where I wrote it down. F mu of x is 1 by kappa x plus mu times u minus f of x over mu times something. So as mu goes to 0, this quantity will go to the directional derivative, which is why I ended up writing this thing here, that at 0 this is what the derivative looks like. And it's at this point it's an exercise for you to show that if f actually happens to be differentiable, then this integral actually yields f of x, the true gradient, which means instead of using the true gradient, you are just generating these random u's and using directional derivatives in the direction given by those random u's. And these directional derivatives you can sort of simulate with your finite differencing or whatever, but really as the finite differencing window goes to 0 and you actually have the true directional derivative and you have infinite number of Gaussian samples, then your gradient of the smoothed guy or the gradient of this randomly estimated guy actually becomes equal to the true gradient, which gives you more confidence in this smoothing method, or sorry, this method of generating directional derivatives in random Gaussian directions. And what happens is that if f is convex and Lipschitz, we already saw that then f of mu belongs to is a CL1 function with a sort of pseudo reasonable Lipschitz constant, and in fact, yeah.
Just to be clear, so is it exactly equal or is it just parallel? It just seems a bit unbelievable, but yeah.
It's equal to that. That integral, if you evaluate that integral, the value of that integral is that. So what you might actually say, okay, it is almost everywhere equal to that, which means in my language equal. That's what it means, right? An integral is exactly equal to another quantity is the same as saying up to a set of measure 0 they are the same. That's what it means. So interesting quantity fact that happens, we showed that it's Lipschitz continuous, and in fact one can flip that around and show that the perturbed gradient, the gradient of the smoothed or the perturbed guy, is essentially a perturbed subgradient of the non-smooth function. So you can use it in place of an honest subgradient up to, so you'll have a subgradient with error epsilon. And that error epsilon is given essentially by the Lipschitz constant that comes up for f of mu. But this is just summarizing what we have seen so far about Gaussian smoothing and using, showing that it's differentiable, getting its Lipschitz constant, and showing that the gradients of the smooth guy are reasonable objects. And now you actually, if you were to use, how would you use these smooth functions in an actual software? How would you implement that, right? That remains to be seen. So far, this is just to give us intuitive and moral confidence that, okay, smoothing is not completely crazy, that's all. And there are a couple of ways of using those. I'll just mention there is no time to go, the algebraic details are slightly heavy, means they're all simple, they're in the nest of paper that I showed you. But it's just good to maybe look at the summary. So now, so far, say when we did optimization, we looked at two types of optimization, right? Deterministic or stochastic. And within deterministic optimization, forgetting the coordinate descent part, which I didn't really honestly cover, you either looked at gradients or subgradients. We didn't really look at Newton style methods, which requires even Hessians. And we also looked at stochastic optimization, where you don't necessarily have access to an oracle that generates gradients or subgradients, but just maybe noisy samples of these guys, which in expectation equal the true subgradients. Here we are looking at, in some sense, what is called a zeroth-order oracle, where the oracle cannot throw back a gradient or subgradient at you. It can only evaluate your function at a particular value. And we use that oracle, that's why it's called the zeroth-order oracle, to simulate the notion of a gradient. So one is this finite differencing oracle. You just generate mean zero, whatever variance you want based on how well you've estimated your parameter space. That can also be the identity matrix. So you generate that G of mu. There is another kind of finite differencing. If you read the article on finite differencing on Wikipedia, it shows that these types of finite differences which look on both sides, like central finite differencing, not only one direction but on both sides of x, minus mu to the left, plus mu to the right. At least these are numerically, in the numerical analysis world, these give slightly more accurate. Complexity theoretically, they don't change anything. From a numerical analysis perspective, people prefer to use these finite differences. And the third is this oracle, directional derivative oracle. And Nesterov mentions this really because directional derivative is, you can say, much weaker object than, it's much cheaper, you can say, maybe object than gradient. And it's not entirely true, because suppose I could get, so if f prime x u is a directional derivative, this actually means gradient of f in direction u. If I were to pick n different directions, I can extract the entries of gradient, but that's order n times expense. But if you optimize using just this guy, you're not paying that full expense. But implementing this oracle, maybe that's why simpler in a certain direction. But most of the time I would just implement one of these guys, which also is quite interesting. Theoretically, there are stronger results available for this particular oracle, but practically, even these perturbed versions, the finite differencing versions which were your first suggestion, they seem to work quite well. But the theory for them is more pessimistic, and it's an open problem in Nesterov's paper to try to understand why the finite differencing guys work empirically much better than the pessimistic theory. So he of course does mention that these two oracles are more suitable for smooth functions, because this is essentially, this shows up here in the, and he also mentions quite interestingly, directional derivatives are usually very easy to extract even for non-smooth, non-convex functions. So if you can somehow simulate directional derivatives, you can also apply this Dfo to purely non-smooth, non-convex problems. So standard Dfo algorithm, which is no surprise, this is exactly the algorithm that you would write down given whatever you have been looking at in this class so far, right? And you minimize that, and at iteration k generate some Gaussian random vector and query your random oracle, get a sort of, let's call it a pseudo gradient, and then update. You can even think B is identity. It's just a gradient shaping matrix which you can shape to your numerical advantage. It's in there because numerically when people write code, they like to rescale gradients and do things to make things converge faster in practice. That's why it's just left in there. So this is essentially nothing but projected subgradient method, right? It's kind of disappointing that we start the class with projected subgradient and we are ending with projected subgradient. Where is the progress in between? So it just happens that a lot of things start looking like subgradient method. In fact, I didn't talk about that, but the ellipsoid algorithm which is the one which is cited for being the first method which gives you complexity theoretic analysis of convex programming. It is because of the ellipsoid method that people started saying convex programming is polynomial time activity, weakly polynomial because it depends on an epsilon. But that method is again nothing but essentially a subgradient method with careful subgradients. So subgradients are a very universal object, which is no surprise, right? Because they help us. We also long back looked at a theorem which showed a function is convex if and only if it's subgradient set, etc., stuff like that. So, it's no surprise that we still are looking at stuff which mimics that subgradient style iteration. The beauty is in being able to not use exact subgradients, but something which looks symbolically like a subgradient and still managing to make the thing work. That requires the hard part here. So the method, you just run this method. Let's call this R of mu. R of mu is just randomized oracle parameterized by mu. If mu is equal to 0, then we are using the directional derivative. If mu is non-zero, then we are using one of these guys. So that's the method. R of mu uses that. So R of 0 is the one with the directional derivative. You generate a random sequence and you try to now to analyze how well does that randomized method or how well does that method perform. You wish to analyze in expectation after all these random samples for simulating your directional derivatives or subgradients, whatever, how much progress have you made? So in expectation after k steps, there is a master inequality rather after t steps. I'm not going to prove that, but this might remind you of a similar inequality that we saw when analyzing subgradient method. Or rather, I just actually presented the analysis of stochastic subgradient method where there was a similar inequality. Point is, reaching this inequality requires a little bit of work, but it's not so critical, except that if you were yourself creating all these methods afresh, what are the guiding principles, right? You started to make stuff look like subgradient. Well, now you start to make your analysis look like subgradient methods analysis, and maybe with a little bit of further algebraic effort, stuff will go through. And that's pretty much what this does. The details are in that paper. They're not so critical here. So you count the total amount of progress. You bound it in terms of step sizes. And now you just have to select a good value of the step sizes to see what is the overall progress. So like in the stochastic subgradient method, when we did stochastic optimization, it was easier not to analyze values at x of k, but rather to analyze values at x hat of k, which is the average iterate divided by weighted by step sizes. So here actually average is easy, but before average, let's try to make a simpler statement. If you maintain the best value attained so far after t steps, let's call that x hat of t. So what we'll try to show that the best value in expectation is upper bounded is order 1 by root t. So that's like non-smooth subgradient method proof. Except something really nasty happens here, which I'll comment on. So the best value is going to be upper bounded by the average value, and then you just take expectation. And the previous master inequality that is shown on the previous slide, that yields this upper bound for you. And now you can pick the best possible step size to make the right hand side as small as possible. The right hand side is just a simple convex function of h of k for a fixed t, so you can get that. And you get best step size, which yields that in expectation you get to within epsilon of the true answer in order 1 by epsilon iterations, where unfortunately the number of iterations, even though it is order 1 by epsilon, it has a dirty thing inside the order, it is dependent on the dimension. So for high dimensional problems, this is not so nice. I don't remember those of you who are working on coordinate descent. I think in coordinate descent analysis there is also dimension dependence in the bound. Do you remember? Do you guys remember, those who are working on coordinate descent? I think
it's kind of it's not like type because the bound depends on the distance between the initial point and the.
Well, that is here R square.
Yeah.
But dependence on dimensionality.
No, other than R square.
Okay.
R square is.
So here this unfortunate thing happens that without having access to an oracle that can compute true gradients, because you're simulating the gradients, in the worst case you slow down by a factor of the dimensionality. All the other factors are exactly the same as in the subgradient method. So this price in terms of dimensionality seems to be irremovable here. But in practice, this bound turns out to be sometimes too pessimistic. So in practice, it's not so bad. And for then, this is like a theoretical guidance, but and this is the kind of result I would go with. There are other theorems in the paper which you can go through, which actually work not with that directional derivative oracle, but with those finite differencing oracles. Here something even nastier happens, which, and I don't like the final result, so I'm not looking at this result in too much detail, but it's still important to mention it here, that you go through exactly the same kind of analysis that's for the directional derivative case, except in the end, to get to within expectation to within epsilon of the truth thing, the number of iterations now depends quadratically on the dimension. This is really terrible. So if your data is more than 100 dimensional, you can already begin to see why these things theoretically already are kind of disappointing. And empirically, however, it doesn't behave so poorly. So there's a gap between, it could still be that this n plus 4 square is not removable in the worst case. That could easily happen, but it could also happen that for a reasonable class of assumptions, you actually don't end up having to pay such a high penalty. But so that's the gap in the analysis that is not yet removed.
So it would be like I was thinking that a lower bound on all these methods would be an interesting thing to.
So yeah, means the obvious lower bounds that apply are maybe the ones that Aditya talked about. He talked about zeroth order lower bounds, first order lower bounds. So if he talked about zeroth order lower bounds, all of those immediately apply. But you need a more refined analysis.
More closer upper and lower bound, I would say, like the people that do in min-max have a closer upper and lower bound, and which means that the order is the same on both sides.
Yeah, so I don't know. So this is a consequence of the kind of oracle you assumed. See, lower bounds are analyzed in a computational model. You endow your oracle with certain computational capabilities, and based on those capabilities you come to some bounds. Now it could be for a certain nicer class of functions, you could get better upper and lower bounds. So you have to really, the lower bound applies to the entire class, and what I'm trying to say is this is too pessimistic. It might be more interesting to make these things attractive, to identify a smaller class of functions for which our results are not so pessimistic. Because this is what we did when we started looking at ordinary convex optimization. You looked at non-smooth functions, you got 1 by epsilon square for subgradients. You assumed smooth function which is once differentiable with whatever Lipschitz constant, you suddenly got 1 by epsilon. And you assumed some more, and then you came up with a cleverer method and you made it 1 by square root of epsilon. That's the optimal gradients method. And these are still sublinear. And then people said, okay, let's assume even more crazy structure. They assumed strong convexity, and suddenly they got linear rate of convergence. So by assuming different structures on functions, by looking at some subclasses, you can maybe improve the nastiness here. But it's kind of very disturbing to see n square here, nevertheless. Okay, the same thing what I've been talking about so far applies also to stochastic derivative-free optimization. And actually Nesterov's paper has even more stuff that can be covered here. He even gives an analysis of non-convex derivative-free optimization, which is quite interesting. Means since 2011 there has been more progress in this area. Okay, there have been a couple of papers at NIPS, and there have been other papers by people in optimization who have made some more progress in analyzing stochastic zeroth-order problems and so on. But fundamentally not too much new stuff.
So you mentioned that if you use any other smoothing, it doesn't make much of a difference. Is that like...
Oh, maybe that was too broad a statement. No, I said if you use non-Gaussian smoothing?
Yeah.
No, it means it should make some difference because, for example, these moments that we were bounding, they came from the Gaussian, right?
Yeah, exactly.
And
Because like this dimension dependence always comes up when you use like Gaussian.
Yeah.
So like can we like analyze like more like you don't use a Gaussian smoothing but something in between.
So that's an interesting question. That's why I said let's not ignore the components that are under our control. The black box f of x is not under our control, but the smoothing is under our control. So you could come up with maybe a nicer smoothing mechanism. So I don't know means what are the standard tricks that people use in statistics to weaken the dependence on dimensionality, but you could borrow some ideas from there. I think in the best case, you will still have at least, I don't know, d to the half or d to the 1/4 or something, n to the half or n to the 1/4 dependence on dimension. But
I was thinking like more when you have some kind of like sparsity or like you know certain part of the function it's smooth and certain part is not smooth. And you have more idea about the function.
so there's a slight conflict of as in formulation here, because suppose f is non-smooth, you smoothen it, now it's smooth suddenly. But you're saying if the black box is not entirely a black box, you could maybe do something better. So there are like several avenues. So if the black box is not entirely a black box means I'm changing, I know a little bit more about my class of functions. Maybe I can improve things. But I like the other idea that you mentioned slightly better, that suppose we stick with this generic class, or even say assume f is differentiable, but smooth it more nicely so that our dependence on dimension is somewhat better. And then it's up to you to construct a smoothing density which allows you to do that. But the trade-off might show up in some other place, right? This bound might improve, but something else might suck. Like a Lipschitz constant might become worse, something might. But it's definitely worthy of investigation. But so far in ML, because of these terrible kinds of bounds, these things haven't gained much interest. But maybe someday, after enough progress is made, people do care a little bit about these. But all I'm saying is whatever I said, by replacing those randomized oracles with this randomized stochastic oracles, the same methods with same type of analysis also work for stochastic Dfo. And it's actually a very good paper if you want to once exercise how to do proofs of subgradient style methods for the entire spectrum. smooth, convex, stochastic, non-convex. You can go through that entire exercise and you will know how to do convergence proofs for that entire spectrum, including also you can do the same kind of thing for accelerated gradient method also. So you can also construct an accelerated Dfo, which is also quite curious. But so again, yeah, so here in the stochastic case also is terrible dimension dependence. So the things that I didn't, we already talked plenty about can that be improved. But other things that, okay, fine, dimensionality is expensive, but maybe we can compensate for that a little bit by trying to just scale up our computational power a little bit. Can we say something more meaningful? And the fifth one has been an open thing because of the kinds of problems, but we might get to see some progress on that depending on what you guys create.
I think people in machine translation, I think it's really cool.
Okay.
Because like they have this crazy evaluation matrix, the cruise code.
Mm-hmm.
So like you tune the parameters of your translation model, and the evaluation matrix is like the overlap between the generated translation and the reference translation.
It's not a black box, right?
So it need not be, remember, black box is just one way of saying it. The other thing is, if it's just too expensive to compute a gradient, then also you can consider simulating a gradient, right?
But then would these all things hold? Because
So, okay.
the idea was that the oracle gives you the exact thing, right?
Sure, but the thing is, suppose it's the classical trade-off in computers, right? Between accuracy and speed. So you have to balance your desires there. Like maybe by just simulating a gradient, you can run the whole procedure 10,000 times faster, but maybe slightly less accurately. And that's the entire reason of success of stochastic methods actually in machine learning is exactly this trade-off. So, but it's worth thinking about a little bit that can we maybe do something, and this difficult setups, or means to my knowledge, most people who work with complicated simulators, where to even get one value of f requires heavy computation. So you cannot even imagine getting gradient of f. That's where people have most typically used this, but those people are running simulations which run in anywhere from 3 to 20 dimensions. Okay, so nice paper which is also on the class webpage. You should all of you should have definitely looked at that paper, but this all the proofs that I mentioned are from Yuri's paper, which is a really nice paper to read. And I guess Dfo is lesser known, so I decided to cover it in the class. And on Wednesday, I will really not spend too much time because Wednesday I want you guys to do the presentations. I will just maybe mention a list of topics which I would have liked to cover, but I couldn't cover, in case anybody is interested in knowing about those topics. Once you know the keyword, then Google can educate you fairly rapidly. Okay, see you tomorrow. So whoever is ideally, no, not ideally, everybody should plan to show up for the project presentations, whether you're presenting or not. So it would, just because if you're not presenting tomorrow doesn't mean that you don't show up, okay? It's very rude to your classmates, and it's also detrimental to the class because we want the people who are presenting to have an audience. Same thing will happen to you on Wednesday.